All right, we're going to look at the stereochemistry of a Diels-Alder reaction that uses cyclopentadiene as a diene. Okay, when you use a cyclopentadiene, now we're going to get two isomers, a Diels-Alder product, but they are isomers. One is endo, one is exo. Let's talk about what is endo, what is exo first. Okay, if you remember the in a chair conformation of a cyclohexane, we use the word axial and equatorial to identify the position of a substituent on a cyclohexane ring. Okay, in this case, we're going to use endo and exo, and here's how it works. When a cyclopentadiene interact, we are forming two bicyclic compound. Okay, this bridge. So take a look at the bridge. This bridge got is a two carbon bridge. This bridge is a one carbon bridge. The endo and exo indicates where the functional group or the substituent is relative to the two carbon bridge. Take a look. The two carbon bridge right here. Endo is closer, exo is further away. Okay, so that's endo and exo. Now let's do this. So since we get two products, we're gonna talk about the major, the minor product now. Okay, but before that, let's take a look at the stability. Which one do you think is theoretically hindered? The endo, exo, or which one is less stable? That's what I mean. Well, some of you probably will guess this right. The two carbon should have more stickily hindered, so the endo product should be less stable, okay, than the exo. All right, because the two carbon versus one carbon, so the sterically hindered side is on the two carbon bridge. Okay, so basically my point is exo product is more stable. But here's the thing though, observation, the endo product is a major product. Voila. What's going on in here? Well, it's nothing new. We talk, if you remember the kinetic product and then the thermodynamic product, we realized that the the endo product is actually the kinetic product, okay? And the exo, which is more stable, we call it thermodynamic product. And I'm not just lying to you. I'm just like, just make this up. People do experiment. I'll give you one experiment right here. They want to see that if exo product is actually the more stable product or not, a thermodynamic product. Well, how do you conduct the experiment and test if the exo product is a more stable product or a thermodynamic product? Well, we're gonna run the Diels-Alder reaction and use the thermodynamic control and see what do we get. If the exo product is actually the more stable, it could become a major product under thermodynamic control. Okay, and all right. So what's thermodynamic control again? What's condition? Long reaction time and a high temperature. Okay, so we're gonna run a Diels-Alder reaction in a long reaction time. Let it run, right, and then increase the temperature and see who's gonna be the major product. We realized that. Take a look. This is the real reaction. This is from the different textbook. They use furan, which is closer to the cyclopentadiene, and the other one is malonic anhydride, similar to this dienophile. Okay, so we got endo and got exo. All right. Thermodynamic control, which means let the reaction run forever, right? Long reaction time and increase the temperature. We found out that the major product is exo. Okay, so that's confirmed that, okay, it's more stable. That's a thermodynamic product. Endo actually also observed it was formed first, but it got converted to exo later as the equilibrium has established. Okay, so we're sure now the exo product is more stable. That's a thermodynamic product, right? The endo formed first and got converted later to the exo product. So that endo is actually the kinetic product. Okay, now, excuse me, why endo product is the major product though? If you remember, go back to the conjugated diene, right? We have 1,2 adduct and 1,4 adduct. The 1,2 adduct form faster because of proximity effect. This one's similar to that. Let's take a look at a proximity effect, but they call it differently. Okay, so we call this an endo rule. So Diels-Alder reaction produces an endo product, which we call endo rule. The reason is when the diene interact with the dienophile, okay, there is a secondary interaction between the pi bond of the electron withdrawing group and the pi bond is who's about to form right here. Okay, let's talk about the secondary interaction first. You may ask, okay, we have secondary. What is primary interaction? The primary interaction is interaction between HOMO and LUMO, and you actually get the new bond from a new bond right here. That's a primary interaction. The secondary interaction is actually just maybe slightly overlap. Maybe they have interaction, but not actually from the bond. Okay, slightly have interaction between pi bond here and pi bond here. All right, and that makes the substituent is get closer to the pi bond right here. I'll look something like this. Take a look. This is cyclopentadiene. Okay, pi bond right there. And instead also, and this is a dienophile. Instead of the C double bond O pointing out, it's pointing in, right? The inside, and there's an interaction right here that keep the carbonyl group closer to the two carbon bridge. Okay, if this one, if the substituents pointing out, the C double bond O pointing out, there's no secondary interaction, but it's more stable because it's less sterically hindered. So it's more stable, but takes longer to form. Okay, so basically you're going to see the energy diagram like this, right? The endo products form faster because the lower activation energy, there's a secondary interaction. Okay, but the exo product is a thermodynamic product. It's more stable because less sterically hindered. Okay, that's the reason why under kinetic control, which is mostly our Diels-Alder reaction is under kinetic control, the endo product is a major product. Okay, so go by endo rule. All right, next video we're gonna do some problem. You have to be able to predict the product under kinetic control. Okay.